How are you doing? How are you doing? Fine, Alhamdulillah. Okay. Today we will start chapter 3, but before this, I'm going back to example 219, 220, sorry. I'll explain to you something we missed last lecture, okay? Okay, so I will share the example. Can you see example 220, okay? Not yet. Example 220, IP address. Can you see my screen?
Yes.
Someone said yes, others said not yet.
Yes.
Yes, okay.
Yes.
Okay. So I will explain to you again example 220. This is about the IP address and how the data is transmitted from the sender to the receiver. So in the example, we see 3 LANs, which means 3 local networks. We said last lecture, when we transmit at the same LAN, like the previous example I will show to you, this one, the transmission, the sender and receiver are on the same local, the same LAN. So they don't need to use the IP address, they only use the physical address or MAC address. When we say MAC or physical, we mean the same. Physical or MAC address in the same LAN, in the local area network, we use for transmission from the sender to the receiver the same MAC or physical address. We don't need to use the IP address, okay? Then, let's go back to, what if we want to transmit or the receiver on other network? He is not on the same local network. So we have to use the IP address. So in our example 220, sender, which is physical address is 10, A10. You saw computer, this one is the sender, and the last one at the bottom is the receiver. The sender is 10, has MAC address 10, or yes, and the last one is the receiver, which has the number, the physical address 95. So how the data come? It comes from the upper layer. Please focus on A10, the sender. The data comes from transport layer, comes from upper layer, which is transport layer. It is involved in a packet. In the network layer, we said it is enveloped in a packet. The packet has the IP address of the sender, which is A, the IP address of the sender, which is A, and the IP address of the receiver, which is P. Here in the bottom, on then LAN 3, the bottom is the receiver. The IP of the receiver is P. Okay? In the network layer, the data is enveloped in a packet. And from the network layer to the data link layer, the data now is enveloped in a frame. So to transmit the data to another local area network or to the other LAN, we have to add in the frame the physical layer of the receiver on the other LAN. We cannot use only the IP address. The IP address, so from the network, we have the IP address of the sender, the IP address of the receiver. This packet is enveloped in another frame which has header in this one, in the pink, it is the header, and the trailer. What's the mission of the header? It has the sender physical address, which or MAC, which is 10, and the receiver MAC address. Now it is 20. 20 is the physical address of the receiver. This is what we see in the header, in the pink color. What is the mission of the trailer in the frame? The trailer for checking that the data is no change. The data which we want to send is the same. In the next hub, the data will be examined through the trailer. Okay, so the trailer mission is to check for the data correction. The data do not altered. Nothing happened to the data. The data comes from the sender to the receiver is the same. How this can be checked through the trailer, through some mathematical function. Okay, so we have now the physical address in the frame, in this frame, the physical address of the next receiver. The next receiver is router 1. Through the physical address, the router and the gateway, through the gateway of device number A10, the gateway of it is router 1. Router 1 has multiple networks and has multiple interfaces. Each entrance here to the router is, we call interface. It has interface with local area 1, with LAN 1, another interface with the upper, this one is another network, and this one is the network 3. So the router here, router 1 connects 3 LANs, 3 networks. The gateway between router 1 and the interface between router 1 and device number A10 is this one. The MAC address is, the physical address is 20. This is the gateway for this device. So the frame now arrived the next destination, which is router 1 with the frame. The data as it is enveloped in the frame arrived. So router 1 now, through the table in the router 1, through the table, the transmission through the IP address, we send the frame through the gateway router. So MAC address for the gateway is 20 now. The physical address there is 1 hop. The physical address can work for only 1 hop. So this physical address, when arrived to router 1, has no work. Now we have another hop to go from router 1 to router 2. How router 1 knows that how to send the data from the receiver to the sender? It has a table. It has a routing table, and from the IP address, it determines where is the next hop. So through its routing table and through the IP address of the receiver, it determines to send the frame, envelope the frame again, envelope the data, the same data in another frame. So this frame mission now ends. We have now another frame. What the new frame has? It has header and trailer. The header has the MAC address of the sender and receiver. The MAC address of the sender is 99. Please note that we put the sender first, the receiver 33. The MAC address for the receiver is 33, which is this one, which is router 2. And the MAC address of the sender, which is router 1, is 99, this interface. And the trailer, again, the trailer to check for the correction of the data. So this frame now sent to the next hop or to the next receiver, which is router 2. Router 2 receives the frame, decapsulate. Now, in the frame, we say it is capsulated. Decapsulate the data, check for the correction of the data through the trailer, and decide where to send the data through its routing table and the IP address in the data. So it enveloped the data again, the same data, enveloped in a new frame. This is the last frame, which have the MAC address of the receiver, which is 95, and the MAC address of this interface. So as we see, the router has more than one interface. How it decide to send the data through which interface of the 3 ones from its routing table and from the IP address in the packet. So it enveloped the same data, put the header, which have the receiver, and it now, the receiver MAC address is 95, and the sender is the interface of the router, and the trailer again to check for the correction of the data. We said that an important note that the physical address, as you see, change every time. The physical address is changed every time, every hop, but the IP address do not change. Why? Because the data should go from the sender to the receiver. And how it know the receiver? Through the IP address. So the IP address cannot be changed, but the physical address can be changed. And how many hops the data takes? It can take 1, 2, 3, 4, 5. It can have 10 hops. It depends on where is the sender and where is the destination or the receiver. So at last, the data arrive the destination receiver with the MAC address 95. The receiver decapsulate the data and check through the trailer that the data is not changed and the data now is arrived. Is this example clear? Did you understand how the data transmitted through the network and not the only LAN? It's globally sent from the sender to the receiver. Do you know now how? Is it clear? Can I have your answer? Is it clear? Yes? Okay, you can go back and make the journey and look at this note in the red. This is the MAC address, and this is the IP address for what? For the upper network. So this network MAC address 44, this interface. So each interface have MAC address. This one, this interface for the router has MAC address 99. This one has 20. And the letter this one have is the IP address. Okay? Fine. I'm sorry, but I noticed that I have to go back to this example. Now, we start chapter 3. Ready? Ready?
Ready.
Ready.
Okay, good. Chapter 3 talks about data and signals. So what we send through the network, we send data, right? And the media which hold this data, we call it signals. Okay? You can see my screen?
Okay, doctor.
Yes.
Okay. Okay. So we are going to learn the types of data, the types of signals, and how the data is transmitted through the network. So to be transmitted, data must be transformed to electromagnetic signals. We know that the data have many forms, but cannot be transmitted in its original form. It should be transformed to electromagnetic signals to go through the network cables, right? Or the network media. So the data can be what are the forms of the data? The data can be analog, can be digital, can be analog or digital. The term analog data refers to information that is continuous, and the digital data refers to information that has discrete states. So the analog refers to the information that is continuous, and the data refers to information that has discrete states. Analog data take on continuous values, and digital data take on discrete values. We will see example. Data can be analog or digital. Again, analog data are continuous and take continuous values. Please close the mic. Please close the mic. Okay. As an example for continuous data, the digital, the analog clock. This clock has the hour hand, the minute hand, and the second hand. This one, so the analog clock is an example for the analog data. So when we want the time now, it is continuous 4 or 3.99 minutes, some 40 seconds, and so on. But as an example of the digital data, we have the digital clock. It is suddenly go from 10:33 to 10:34. So we have discrete values for the digital data, okay? This is an example. To differentiate between the digital data and the analog data. This is analog data and this is digital data. Signals can be analog or digital also. The data is transmitted through signals, and the signals can be also analog or digital. Analog signals can have an infinite number of values in a range. Why? Because the data in the analog signals is continuous. So it has infinite number of values. But the digital signals can have only limited number of values because it is discrete. So the analog signals can have an infinite number for values, and the digital signals can have only limited number of values. This is another comparison of the analog and digital signals. As you see, the analog signal is continuous, and you know between each point we have infinite values between each point and another point. So analog signal is continuous, have different and continuous values, different and continuous values. Compared to the digital on the other side, the digital signal have like steady values. It has different limits, but it is steady values. And it is also discrete. It is not continuous. This is a comparison between the analog on the left side, or A of the figure, and the digital in the right side, the digital signal. Okay. In data communication, we commonly use periodic analog signals and non-periodic digital signals. Periodic analog signals can be classified as simple or composite. Simple or composite. We will see an example for simple or composite. A simple periodic analog signal, like a sine wave, cannot be decomposed. What we mean by simple? By simple, we mean that this wave cannot be decomposed into a simpler signals. A composite periodic analog signal is composed of multiple sine waves. A composite periodic signal is composed of multiple sine wave, and we will see an example. This is the sine wave. This is the sine wave. This one is a composite. Each one is a simple sine wave. So this one is one signal. This is another signal, and this is another wave. So this signal have how many? 1, 2, 3 waves. 3 waves over the time here is not specific. It can be 1 second here, can be 1 second. Here, two signals. We have two signals, A and B, with the same phase and frequency. Same phase and frequency, but different amplitude. So we have a new concept, which is wave amplitude. By amplitude, we mean the peak or the height. This one is the amplitude. So in A and B, we have the same phase and frequency, same frequency. What we mean by frequency? The frequency is the number of waves in the time unit. So here we have 1, 2, and 3 waves. And here also we have 1, 2, 3 waves. So we have the same frequency, but we have different amplitude. This amplitude is different from this amplitude. The amplitude here is more than in the signal B. This is a high peak in A, high peak amplitude, and in B we have low peak amplitude. Is it clear?
Doctor.
Yeah, I want you to know what is the wave, what is the frequency, and what is the amplitude. All of this is clear for you. Okay.
Doctor, can I ask something?
Again, please.
Can I ask a question?
Yes, of course.
What does low or high peak amplitude means?
Yeah. It is the peak, which is the height of the wave. So different waves have different amplitude. Amplitude is the peak. It's a concept for the wave. It's a attribute for the wave. The wave have, the signal have a frequency, have amplitude, and have time. The amplitude is the height, okay? In simple meaning, it's the height of the wave, okay?
Okay.
So here, the height or the peak is more than the figure in B. Understand? So the amplitude, you can say the height, okay? Understand?
Yeah. Thank you, Doctor.
You're welcome. Now, what is the frequency? The frequency, as I told you in the previous example or figure, the frequency is the number of the waves in the time unit. So if we said here we have 1 second, sorry. If we have here 1 second, so the frequency now is 1. This is 1 wave. This is 2 and 3. So the frequency is 3 hertz in 1 second. And it's the same frequency in the other. So Frequency and period. By period, we mean time. The signal have period and have a frequency. Frequency and period are the inverse of each other. So frequency equal 1 over t, which is time, and time equal 1 over f. It is inverse of each other. It's a rule, okay? So here in the example, we have two signals with the same amplitude and phase, but different frequencies. Different frequencies. So if we count here, as you say, the first one is one wave in the signal. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. We have 12 waves in the signal per 1 second. So the period is 1 over 12 second. That's how we calculate the period. It's 1 over the frequency. The frequency, by how we know the frequency? We count the waves. The waves are 12. So 1 over 12 is the time. So the frequency is 12 hertz. And the period is 1 over 12 second. Understand how we calculate?
Yes.
It's so easy, so simple. Okay. The amplitude is the same, which means the height of the wave is the same in the two figures. But we have different frequencies. In figure number B, 34 number B, as you see, there are less number of waves. So in the same signal, we have 1, 2, 3, 4, 5, 6. We have 6 waves in 1 second. So the period is 1 over 6. Is it clear how we calculate?
Clear, doctor.
Yes?
Yes, yes.
Okay. Please mute. Mute, please. Okay. Now this table shows the units of period and frequency. So we say, for example, we have a signal which is 1 hertz per a second. I will draw for you. This one, let's say, for example, 1 second. So we have this signal is 1 hertz per a second. So we will use this table to solve multiple examples. This shows the units of period and frequency. For the period, which means time, we have 1 second. We have millisecond, ms, millisecond, which is equal 10 to the power minus 3 of the second. And we have microsecond, which is 10 to the power minus 6 of the second. And we have nanosecond, and we have picosecond. Nanosecond, 10 to the power minus 10 of the second, and picosecond, which is 10 to the power minus 12 of the second. This is for the period. What about the frequency? We have 1 hertz, kilohertz, which is 10 to the power 3 hertz, megahertz, which is 10 to the power 6 hertz, gigahertz, which is 10 to the power 9 hertz, and terahertz, which is 10 to the power 12 of the hertz. This table, we will go back to it to solve our examples. So the first example, the power we use at home, suppose the power we use at home has a frequency of 60 hertz. We have the frequency 60 hertz. The period of this sine wave can be determined as follows. We said the rule. The rule is the time is opposite of frequency. We have the frequency, so we can calculate the time or the period, right? So the time equal 1 over frequency, which is 60. 1 over 60 is 0.0166 seconds. And we can convert the seconds to the microseconds by multiply with 10 to the power 3. So it is now 16.6 milliseconds. We calculate the period by 1 over frequency, which is 60. So simple, right? Is it clear?
Clear, Doctor.
Yeah, because we have the rule. T equal 1 over F. Next example. The period of a signal is 100 millisecond. The period is 100 millisecond. What is the frequency in kilohertz? First, we change the 100 millisecond to second. Then we calculate the frequency from the period. 1 hertz equal 10 to the power minus 3 kilohertz. It's the opposite. Please close the mic. نور الفصيحة, please mute. Okay. So it's the opposite. As we see in the table, we said kilohertz equal 10 to the power 3 hertz. But now we want to make the opposite. From hertz, we want to convert to kilohertz. So the 10 to the power 3 become 10 to the power minus 3. And that's what's happening in this example. One hertz equal 10 to the power minus 3 kilohertz. So at the beginning, we change milliseconds to seconds. How? 10 milliseconds multiplied by 10 to the power minus 3, it's equal 10 to the power minus 1 seconds. You know the law, the rule, when we multiply the powers, we sum the powers. So this one, 10 to the power 2, 100 equal 100 equal 10 to the power 2, right? So 10 to the power 2 multiply by 10 to the power minus 3, we sum 2 and minus 3. The answer is, طيب, write in the chat the answer. I want to see who will answer the right, who will write the true answer. We want to multiply 10 to the power 2 multiply by 10 to the power minus 3. Write in the chat. Write the answer, please. Write 10 to the power something. Ten to the power like this. 10 to the power 10 to the power minus 1 or 1 over 10. You are right. You are right. So, Noreen, good. Muhammad is good. Right? No, Noreen is wrong. To the power minus 10, yes. 1 minus 1, yes. Yes, yes. And at the beginning, yes, okay. Good. Good. I want to be sure that you know the rules of the power multiplication. So now to convert the 10 millisecond to the second, we multiply 100 by 10 to the power minus 3, and the answer is 10 to the power minus 1. And our rule law, the frequency is equal 1 over 10 now, which means 1 over 10 to the power minus 1 hertz. Then the question told us want the answer in kilohertz. So to convert to the kilohertz, the first answer is 10 hertz. And to change hertz to the kilohertz, we multiply by 10 to the power minus 3. And the final answer is 10 to the power minus 2 kilohertz. Is it clear? The example is clear? Write in the chat, please. Any question if the example is not clear?
Clear, doctor.
Clear. Okay. Okay, now so, I will stop at this example. So we will stop. First, we read this slide. Frequency is the rate of change with respect to the time. Frequency is the rate of change with respect to the time. Change in a short span of time means high frequency, and change over a long span of time means low frequency. So if we go back to our examples, this is to the hour. Here we have high frequency in A, right? And in B, we have low frequency. If a signal does not change at all, its frequency is 0. And if a signal changes instantaneously, its frequency is infinite. We stop at this slide, 3.17, okay? Okay?
Okay, Doctor.
Okay.
Okay.
Okay, thank you all.
Thank you, Doctor.
Have a good day.
Yeah.
Have a good day. Assalamu alaikum.
Waalaikumsalam.
Waalaikumsalam. Thank you, Doctor. Waalaikumsalam.